Hello again, my fellow EG and Python lovers. In our previous session, we epoched our data using MNE, breaking down our EEG into distinct conditions for more detailed analysis. In this video, we will learn how to compute and visualize ERPs. Well, up to now, we have successfully created our condition epochs, and each condition is now represented by a collection of epochs, providing us with a foundation for ERP and time frequency analysis. Alright, let's assume that our analysis is focused specifically on conditions 1 and condition 2. In this case, we can create a separate variable for each of these conditions. For instance, we'll create a variable named condition 1 epochs for condition 1 and another variable condition 2 epochs for condition 2. We'll extract the corresponding epochs from the dictionary and assign them to these variables. Essentially, by doing this, we are segregating the epochs related to condition 1 and condition 2, storing them with distinct names. Now, for example, if we examine the condition 2 epochs, actually it contains information related to epoch 2 with 78 trials. Let's go back to the beginning once more and see what we have done here. Well, we loaded the data related to labels and stored it in 3 columns under the title EEG events because we needed it later, especially in the epoching section of the code where we utilized it in the MNE.epochs function. Further, we considered the presentation duration of the stimuli and baseline. We initially had 4 epochs encompassing all conditions, and at this point we specifically separated only 2 of them, which are condition 1 and condition 2. Now, it's a good idea to take a look at the data related to each condition. Here we are solely dealing with dictionaries, and we need to be able to access the data within these dictionaries. For instance, if I want to examine the data pertaining to condition 2, I can use the getData command. So here, if I use that get underline data and run the cell, well, it actually indicates that the data belongs to epoch number 2, which comprises 78 trials, and the time points are almost 1000 points. None of the epochs have been considered as bad epochs here, so we didn't have dropped any of our epochs. This means that if it detects an epoch that contains artifacts, it can eliminate them. If you notice that if a significant number of epochs have been removed and you are confident that they are not artifacts, you can make adjustments in the epoch function to ensure that the function is not considered that the rejection is not considered for epochs. So here, if I go to the epochs command, I can use this code, reject equal none, so that the function will not reject any of our epochs. Well, let's return back to our code. What does this number mean, my friends? Well, it represents the time points in each trial. When we define the start and the end of the epochs, specifying a range from -200 milliseconds to 2000 milliseconds, we expect to have 2020 time points in total. However, why do we have half of it here? Well, this discrepancy arises because our sampling rate is 5000 Hz. Therefore, the number of time points in each trial for this condition, as well as other conditions, will be half of the 2200, resulting in 1100 time points. Okay, I'm highlighting this section, and you tell me what this part of the data represents. And similarly, what do others show? Please pause the video for a few seconds and think about this question. My friends, what we see here is almost 1000 data points here for each trial in the first condition of our experiment. And we have this data for all electrodes. Let's take a look at the shape of the data altogether. So here at the end, if I type that shape, what should we see? Now, we have a substantial amount of data. Here we have 78 epochs for condition 2, for example, 19 electrodes in the middle, so it has the data for all electrodes, and approximately 1000 data points so far. Okay, we can be confident that we have successfully separated the epochs. If we also want to check the shape, for example, for condition 1, we can use condition 1 epochs variable here and see that the only difference is with regard to the number of trials. Everything else should be relatively consistent with condition 1. Well, if we take the average of the get data that we access, we can easily obtain the ERPs or event-related potentials. Moreover, on the same data, we can also explore time frequency information. However, before that, we want to access the data related to one of these, and let's say, for example, the 8th channel, assuming it represents only one channel. When using get data, I can use square brackets here. So if I use square brackets and then write 8, actually I'm specifying that for all epochs for the 8th channels and for all time points. So I will have all time points for the 8th channel. So if I write get data number 8 here, it provides information for 78 epochs only for the 8th channels. This means if instead of 8 I put here a column, it will give all data for all channels. And if I specify the channel index, say for example 1 channel, it gives me data for 75 epochs for that electrodes. So we have 78 of these data, and I'm highlighting here 78 of these data. And also the shape of this indicates that it is for only for one channel if I use number 8 here. Now, we usually consider a specific and separate channel towards the end of our analysis to perform EEG or time frequency on. So to access the data for a single channel, I can use this command. Additionally, if I want to access only the first epoch for this channel, so I can use another command. So here I will type 0, 8, and then for all data points. It means the first trial, the 8th channel, and all data points. So this command will give me only almost 1000 data points for the first trial. The middle number here is the channel index, and I will explain how we can find the index from the channel name later. Well, in ERP analysis, we take the average. So here from the data we have in actually condition 1 epochs, we take the average and store it in a separate variable. Here we extracted the variable name related to the epochs of condition 1, and all we need to do is to use the average function after the variable name. This command takes the average for each channel across all trials and stored it in a variable. Now, we can check the contents of this variable. Well, if I see the contents, I can see it is actually the kind of the data is average, and it has taken the average for condition number 1 for 19 electrodes here with 75 trials. We can store this in a variable named called ERP, which is essentially what we need. And similarly for condition 2, we can do the same, resulting in the ERP related to condition 2. The next step is to plot the averages, the averages obtained for 19 channels and 75 events, in a way that each channel has 75 events, and we can visualize the corresponding averages in a plot. So let's assume that here we want to perform the final analysis on channel FZ, with 75 stimuli of condition 1 have been presented here, and we have 75 epochs for one electrode FZ. What we've just done for these trials is take an average, obtaining the ERP for electrode FZ. So here we have ERPs for 2 conditions. Usually we are interested in the ERP of a specific channel. To find the channel precisely, we can use functions I mentioned earlier regarding EEG data. First, we need to know the names by, for example, using the chnames command, eeg.ch_names. So we can here see the names of the channels. For example, if I want to use FZ channel, I should use this title FZ line AV. So I put it in a variable. Afterward, I need to determine the index of this electrode, which I count from 0, 0, 1, 2, 3, 4 will be 4. How can I find this index? Say for example, index number 4. Here we have created a variable, named it channel for analysis, and transformed the noun channel name into this variable. In MNE, there is a keyword called peaks that actually specifies the desired channel. Here we have created another variable named myPeak, representing the channel I intend to extract. And I also instructed MNE to go through the CH names in the EEG data info and find the index of that channel, then transfer it to the myPeak variable here. Well, this code snippet allows me to find the index, for instance, index number 4 corresponding to the channel of interest. Alright, here we have extracted the index and assigned it to a variable named myPeak. Note that ch names is a text variable representing names or labels of the channels in EEG data. With this code, we aim to extract the corresponding number or index for that channel. Now, let's assume that we want to extract the ERP only for the channel FZ. So in this continuation, when we were calculating the average, for example, for condition 1, we were computing the average ERP. When we provide myPeak as an argument here, it indicates that we want to calculate the averages only for our chosen electrode. If we provide average without any input arguments, it calculates the average over all electrodes. However, specifying myPeak here means we are calculating the average ERP specifically for the electrode with index number 4, which in this example corresponds to the FZ channel. So let's run this cell, and in the next step we are going to plot these averages, and the plots you see here are specifically for channel 1 and for condition 1 and condition 2. Note that these deviations seen in the signal, if for example there were 30 participants, the plot would be smoother, similar to what we discussed in theoretical discussions about them. Usually ERP analyses are conducted in intervals shorter than 2000 milliseconds, and shorter intervals are considered for a specific analysis. For instance, for the P3 component, a time interval between 250 to 500 or 600 milliseconds is often considered. Alternatively, delayed components may be examined in wider intervals, such as 800 milliseconds. Well, few ERP studies have explored such broad intervals. However, we consider this 2000 millisecond interval to be able to visualize time frequency as well. Why? Because time frequency analysis often involve longer intervals. This topic, my friends, will be covered in the next video. But before we continue, we can also see, let's have the average condition average, not just for myPeak, but for all electrodes, and see what we can observe in our plot. This is the plot for all 19 electrodes. So instead of one peak, we can have the plot for all electrodes for each condition also in our ERP plots. In summary, we've successfully separated our EEG data into conditions, creating variables for each condition. Focusing on condition 1 and 2, we've explored the data associated with epochs, ensuring we have a foundation for ERP and time frequency analysis. Specifically, we examined the structure of the data, ensuring that we have distinct averages for conditions and visualize ERPs for chosen channel. Looking ahead, in the next video, we'll focus on plotting time frequency analysis. Stay tuned and thank you.